In this video lecture, I will introduce the idea or the concept of an error bound in a approximation in general, but in particular, we will talk about midpoint approximations. And let's start with defining what is an error. In our case, we have an integral, and a definite integral that we are trying to figure out, and we approximate it with, let's say, mn. And as we know, well, this could be any approximation, right? So it could be ln or rn, so let's just call it an. And we know that it's not always, or even not always, or never accurate. And we define an error as a difference between what we're looking for and what we think it is. So this is something that we would call an error for this approximation method. And A could be M or R or L, or soon we'll learn the trapezoid rule and then Simpson's rule, so A could be anything. And A is all the different approximations that we've learned. So this is what I just said, I guess. We haven't learned these two yet, but we will. And we can state a few facts or make a few observations about the error. First of all, when e is less than 0, that means we overestimated. And when e is greater than 0, we are underestimating. Now, it is also not too hard to notice that as n goes to infinity, it doesn't matter which method you use, the error should go to 0. This is kind of the whole definition of an integral as a limit. That's just another interpretation of it. Now we can be a little bit more specific about the errors in the left endpoint approximation and the error in the right endpoint approximation. Their product is always negative, meaning if one overestimates, the other one underestimates the integral, which is an interesting fact. And another fact is that we observed is that the error in the midpoint approximation is less than the errors in the left endpoint and the right endpoint approximations. That was kind of one of the reasons why we introduced the midpoint, as it appeared to be a better tool. And now the question that we are concerned with is how large is the error, because well, we don't want to make too much of an error when we're using these approximations. So the question is how big is the error? And this is where the concept of a bound comes in. We don't know how big the error would be in each particular case because we never know the answer. However, it can be established theoretically that in midpoint approximation, the error, no matter what function you have, is always going to be less than the following expression. And in this expression, we already know what a and b are. So a and b are the limits in the integral, so we understand that. N is the number of intervals. We understand that. And the only thing that we don't understand right away is what is k. And k is defined to be the largest value of the absolute value of the second derivative of a function on the interval ab. So basically, to find k, all you have to do is to find the second derivative of your function and find what is the largest value it can be on the interval from a to b. So let's practice using this formula on a problem like this. So in our case, a is 1, b is 4, n is 6, and to find k, we're going to look at the function, then we're going to look at the derivative, then we're going to look at the second derivative, and then we're going to acknowledge that the second derivative is a linear function, and on the interval from 1 to 4, it's going to have its minimum at 1, and it's going to have its maximum at 4. So if we want to know k could be any number that is greater than anything the second derivative can be on this interval from 1 to 4, and we can see that the largest value this function can be on the interval from 1 to 4 is 244. So you can take k to be any number greater than 244. For sometimes to make computations easier, we can just pick some round number, but if we want to be as accurate as possible, then we're gonna have to pick the smallest k that it can be, which is 244. And now we're gonna put it into the formula. So the error the upper bound for the error in this particular problem is, and we plug everything in. I guess let me write the formula once again. So it's k b minus a cube over 24n squared, and in our case it will be 244 times 4 minus 1 cubed divided by 24 6 squared. I'm just gonna grab a calculator, and the answer that I got is 7.625, meaning that whatever number I'll get for M6, I am at most 7.625 units off from the true answer, which we still don't know what it is, right? So in real life we wouldn't know. Here we can of course compute it and verify the formula. Another type of the problems that we can do using this formula is kind of in reverse. We can figure out the smallest value n that will guarantee a certain accuracy. So to do that, we're going to use we're going to start off with a formula. So the upper bound for the error is k times b minus a cube divided by 24n squared. And if we want the error to be 0.01, less than 0.01, so if I want my error to be less than 0.01, but I know my error is less than this. So one way to make sure that my error is less than 0.01 is to pick n so big that the expression that I have in the middle right now is less than 0.01. So this is the inequality that we will be solving for n. And to solve it, it's just a simple inequality. So we're just going to flip this fraction. And we're going to flip this inequality sign as well. And then we're just going to isolate n squared. And the reciprocal of 100 is 100. So here we're going to have k times b minus a cube over 2400. And because everything is positive, so technically there are two solutions, but if we restrict n to only have positive values, then the only solution, the only interval solution is this. Well, the only solution set that we care about is just the square, n is being greater than the radical of this expression. And now to compute this, we again have to figure out what is a, what is b. A is -1, b is 3. To find k, we have to find the second derivative. So function here is this. The first derivative is this. Second derivative is this. And then on the interval from -1 to 3, the smallest it can be is at -1, and the largest it can be is at 3. So the value of this function at 3 is 74. So we can just set k to be equal 74. And finishing computing this, I'll just put it here on the side. We plug everything in. So k is 74, b is 3, a is -1, divided by 2400, and I'm just going to put it all in the calculator. Well, I just realized that I had a 100 on the wrong side. This 100 should be in the numerator. So let me put it there. Or I guess we can keep it in the denominator, but we're just going to have to write it as a 100. And then the answer then becomes, I believe it's 148 point something, I forgot. Actually, 140.48. So this is the smallest n can be, and since n is an integer, the smallest n can be is actually 141. So the answer to the question, what is the minimum value of n that will guarantee this estimate will be within 0.01, the answer is 141. 41. So we discussed what an error is and how to bound it, and how to use this error bound formula in two different ways.